So now it's time to put the washer method into action with this particular problem right here. So we want to calculate the volume generated by rotating the area bounded by the curves y equals the square root of x and y equals x cubed. So I have them drawn right here from Desmos, which of course, if you were doing this by hand, you'd have to draw them yourself first. I would recommend using Desmos as a tool to help you, or whatever, GeoGebra, other graphing tool you're using. And we want to know which one's which. So we want to know which one is y equals the square root of x and which one's y equals x cubed. Of course, I know, but I would like you to be able to see it from here as well. So f of x, which is the square root of x, is the curve that's on the top here. If I turn off the region, you can see. So f of x is the square root of x, which is that one, right? G of x, which is x cubed, is that one. So one's concave down, f of x is concave down, g of x is concave up, at least for that region. All right, and so then we're looking at the region in between the two. All right, so let's label those. This one is f of x, which is the square root of x. This other one over here is, this blue one right here is the x cubed. So that would be g of x, which is x cubed, right there. So that's that curve right there. G of x is x cubed, and this is f of x equals the square root of x right there. Okay, so I've got the region shaded, I've got the graphs drawn, or the graph drawn. I left in the bottom part because what you're thinking about is it's rotating around the x-axis. So it says about the x-axis. So that means this is my axis of symmetry, or excuse me, axis of rotation. Sorry, it's symmetrical for the three-dimensional object. So I'm rotating it around that axis of rotation. And I say using the washer method, but honestly, that's all you would know how to do at this point because you don't know the other method yet. So the washer method is definitely what we would use. So we need to come up with a rectangle inside this. So I'm just going to put it right here in the middle. Why not? So there's my approximating rectangle. Always have to draw those when I'm doing them by hand. And I need to think about the axis of rotation and the distance away from that, because I need to have a small r of x and a capital R of x. And oh, for the record, this is going to be dx, because if this is my axis of rotation, then in the disc and washer method, the rectangle is always perpendicular to that axis of rotation. And that means that we're definitely going to be using dx as our thickness of our disc, or in this case, our washer. All right, now what about the boundaries? Well, we can tell from a mile away, hopefully, that we're going from 0 to 1. So you can see right here, they intersect at 0, and over here, they intersect at 1. So the intersection points for the integration boundaries, if we want to find them by hand, analytically. Now, it wasn't specifically asked for, but just in case, you need to know how to do that. You would set the square root of x, which is f of x, equal to x cubed. And we can all see, hopefully from a mile away, what the answers are, but that's all right. So then you would square both sides to make the square root go away. You'd have x equals x to the 6th, which means 0 is equal to x to the 6th minus x, which is equal to x times x to the 5th minus 1. So either x equals 0 or x to the 5th minus 1 equals 0, which means x to the 5th is 1, which means x is 1. So there they are analytically. Again, it wasn't specifically asked for, so if you want to, you can use Desmos, right? So, or use Desmos if they work out nicely, which these did. So these worked out to be nice whole numbers, so it was no problem. So I have my A and I have my B. I know I'm going to integrate from 0 to 1. Now the only hard part about all of this is when I want to find that volume, the volume is going to be equal to it'll be pi integral from 0 to 1 and then it'll be, let's see here, r of x minus little r of x. So I'm going to need something squared minus something squared. And then dx is my thickness. So I guess I didn't really need to make that so little, but I was trying to say that, you know, one of them is capital R of x. Actually, let me just do it in this color. One of them is capital R of x, and one of them is little r of x. So one of them is larger than the other. All right, so what is capital R of x? Okay, so imagine this is your center, your axis of rotation, right? It's the center upon which you spin this object. So if you want to build that outer ring of that washer, it'd be from the outer portion. So R of x is that distance right there, which would be the distance from the axis of rotation, which is the x-axis, all the way up to that curve, which is the square root of x. So this is the square root of x right here. Little r of x is this distance right here, the distance from 0 to that inner portion of the curve, which is x cubed. Right there. Because for that region from 0 to 1, the square root of x is the larger curve. It's the outer curve when you swing it around the x-axis. Great. All right, so we're done. So now all we have to do is find this. So this is the integral from 0 to 1. Square root of x squared is x minus x to the 6th dx, which is pi times 1/2 x squared minus 1/7 x to the 7th from 0 to 1. The 0 is irrelevant because this is a polynomial with no constant term, so pi, it'll be 1/2 minus 1/7. Oh, minus 0. I mean, if you want to see that. Here, I can do that. So 1/2 minus the 7th minus 0. And 1/2 minus the 7th, that's 7/14 and 2/14. So that would be 5/14. So this is 5 pi over 14. And I think I said it was in centimeters, so it'd be centimeters cubed. Now, if I want a decimal approximation, I can come up with that. Bring this up. And so there's the picture. There's the tulip. It's going to form like a tulip shape when you swing it around the axis. So I just think of it as a tulip. So I've got the rectangle right there. Of course, it could be anywhere technically on that curve. You can put it wherever you like, but I've just put it right in the middle. And then the integral calculations I actually have right here. So from 0 to 1, which is in fact 5 pi over 14, which is 1.122, right? 0 to 1, x minus x to 6. So I could say 1.122 centimeters cubed.